All right, we're into our second day of curve sketching. Yesterday we looked at increasing and decreasing functions and max mins. Today we're going to look a little bit more at what the second derivative is going to tell us. So we're interested in well, in this example, thinking about acceleration at least, we're interested in where the acceleration is making the change over from negative to positive. So remembering back to last unit, what we noticed was the acceleration was less than 0 when the graph was concave down, and the acceleration was greater than 0 when the graph was concave up. So concave down, basically we're just looking for a parabola shape opening down, right? That's what concave down means. It doesn't have to be a parabola, obviously, but this downward shape. So here, that part there is clearly opening downwards, right? And over here, we're definitely opening up. And then from here on, would be down again. Now the tricky part, because I left a little bit of a blank space there in the middle, the tricky part is figuring out where the crossover actually happens. Really tricky to do just by looking at it. I mean, we can ballpark it, which is all I'm going to try and do here. But our job today will be to figure out exactly where that point is. Maybe about there. So right at that point, right at that red point, I'm saying that is where our acceleration would be 0. And remember, your acceleration was the second derivative of displacement. Okay. So the way you find these points is you take the second derivative and set them to 0. The other thing to notice, we're going to mention this in a moment, for the blue ones, where the acceleration is less than 0, the horizontal tangents there are local maxes, right? If the concavity is down, then we're going to have a local max. If the concavity is up, then we're going to have a local min. Okay, and that's part of something called the second derivative test today. The other thing we're going to do is we're going to start our official algorithm for curve sketching. So we're going to do another example today, but we're going to work through it similar to how we did last class. But this time we're going to talk specifically about the things that we're going to do every single time as we try and do a curve sketch. So topic, concavity and the second derivative test. There's a lot here. This is sort of the official stuff that we need to tell you. But I'm not going to spend too much time here. It says the graph is concave up. We've mentioned this before. It's concave up if all tangents are below the function. So if you look down here, right here we're concave up, and you can see all the tangent lines drawn below. Whereas over here we're concave down, and all of the tangents are above. Same thing over here, concave down, and our tangents are above the line, concave up, and the tangents are below the line. And then right here we need this word. We've talked about critical points. An inflection point is a point where our concavity changes. Okay, so an inflection point, or a point of inflection, is a point where the second derivative is equal to 0. And that's what we were finding in that little warm-up, right? Those red dots, trying to find exactly the point where we make the change from concave up to concave down. So yesterday we were finding critical points, which was our maxes and mins, right? Places of horizontal tangents. Critical points we found by setting the first derivative to 0. The inflection points we find by setting the second derivative to 0. So here's what our second derivative does. We've mentioned this, so there's not too many changes here. If the second derivative is less than 0, then it's concave down. If it's greater than 0, then it's concave up. And if the concavity changes, so if we're going from concave up to concave down at a particular spot, then that point's called an inflection point. And at that point, our second derivative would actually be equal to 0. And that's basically what we're going to look for, right? It's hard to look for things and say, is it less than 0, greater than 0? We can check those. But you can solve by setting it equal to 0. And this is what I mentioned in the warm-up, this idea of the second derivative test. If we're wondering if things are maxes or mins, You have to read this really carefully, actually. It makes sense, but you have to read the statement carefully. It says if f prime of a is 0, so that means your first derivative is 0. That means you have a horizontal tangent, right? So if the first derivative is 0 and the second derivative is greater than 0, so here you have a horizontal tangent. That's what that tells you. And here, if the second derivative is greater than 0, then it's concave up. Then the situation we must be in is we must have a local minimum, right? That's what that's telling you. And then similarly on the second one, excuse me, still we have a horizontal tangent, derivative 0. This time the second derivative is less than 0. Then that's a situation where we have a local max. And it might happen that we get 0 both times. And if that happens, then we had a point of inflection. Right? Now that actually would have happened to us in the problem we did yesterday. We didn't go as far as taking the second derivative, but if you remember the way that sort of curved on the left-hand side, we ended up with an extra inflection point there. Okay, we're just going to try. This is a miserable looking function, but it's okay because I'm not asking you to do anything real hard with it. This is not the one that we're going to graph. It says consider the function. Verify that x equals minus 3 is a critical number. So remember what a critical number was. A critical number was an x value where if I sub it into the derivative, I get 0. So it's the location of a horizontal tangent. So if I take the derivative of 20x to the 4, there's our derivative. Still dealing with polynomials, which is kind of nice. And what was I checking? Minus 3. And if I sub all of that in, I get an answer of 0. Right? That's how you're verifying it. Hey, look, it's a critical number because the second derivative is 0. Notice, this wasn't a situation where I would have been real excited to solve it. Right? If we were trying to find the critical numbers, trying to find the critical points, you would have had to take that and set it to 0 and solve. So that would have been a miserable quartic with a lot of long division. But we didn't have to do that this time. We were just verifying that it actually was a critical number. Part B says, okay, now that we know there's a horizontal tangent at minus 3, what situation are we in? Is it a maximum or a minimum? So the second derivative test said, well, we can check to see if it's concave up or concave down. And so that's what we'll try here. We need to get our second derivative. So I'm back up to this line here, taking the derivative of that. That's 80x cubed plus minus 6x minus 4. And we want to know what happens at minus 3. In fact, all we really care about is the sign. Right? I don't care what the number is. I really care if it's positive or negative. Sometimes that helps. Sometimes it means we can just look at it and figure it out a little bit. I don't think I can do that this time, though. So I'm going to make this calculation. Sorry, I was doing that calculation and I just got interrupted there. I think I ended up getting, I'm not sure if this is right anymore after I got interrupted. I got 1687? That sounds 27 times. I'm double checking now, I'm worried. I don't think that's right. Hold on. I need to lock my door more. Minus 27 times. No, I got minus 526 that time. Okay, one of those hopefully is right. So if I get minus 526, that's telling you that it's concave down, therefore concave down. And if it's concave down, then x equals minus 3 must be a maximum. Right? If it's concave down and we have horizontal tangent, then that must happen at a maximum value. So that's how the second derivative test works. You can figure out the location of critical points, and then you can sub them into the second derivative to actually figure out if it's a max or a min. Works pretty good. Okay, here's the one we're going to try. This is our first completely through the process curve sketch. So I've got 6 things listed there that we're going to deal with so far. So y-intercepts and x-intercepts we've already done. Critical points we did yesterday. Intervals of increase and decrease we sort of mentioned but didn't actually do formally. So we're going to do that more carefully today. Inflection points is new today, and then intervals of concavity will be similar to number 4. Now, as we're going through this stuff is the process we're going to follow. So we're not going to skip any of these steps ever. We're always going to do them. And in fact, we're going to have to add in a couple more in the next few days as we start adding in rational expressions where we have to start dealing with asymptotes too. So this is the starting point. This will work for all polynomial functions, and then we'll add in more. But remember, you're not skipping any of these steps. At the end of this unit, we have a test, and the way this test is a very different test than all the other units. The way the test in this unit works is I'm going to give you 3 functions, and you graph them, and that's the whole test. So you have your 75-minute period to graph 3 functions by carrying out exactly this procedure every single time and trying not to miss anything. So it's a lot of practice making sure we don't make any calculation errors, following these steps and making sure that as we're figuring out information, we can make all of the right connections so that we see how everything works together. Okay. So at least this part isn't too bad to get started, right? The y-intercept, the way we find our y-intercept is we set x to 0 and we get an answer of 5. That's how we get our x-intercept, or excuse me, our y-intercept. And so on our graph, I can go ahead and I can put that on right now. We have a y-intercept of 5. So I know that part. I'm sorry, by the way, if you want to do that, if you want to create sort of a graph off to the side already, you might want to do that. I've got an advantage on you because I've done this one already. I know what it's supposed to look like. So I know that this grid is big enough. When you do them for the first time without my help, you probably can't start the grid yet. Right? You'll have to figure out a few pieces of information before you get any further. For the x-intercepts, we're setting the function equal to 0. So it's x to the 4th minus 6x squared plus 5. Set that equal to 0. Now it's quartic, which is a little bit scary, but the fact that it doesn't have any odd terms, it doesn't have the cube or the linear term in there, helps. We can think of this, we've probably done this a few times before, think of it like that. I should put not an x there, I should put a y. Think of it as y squared minus 6y plus 5. And we've just made this substitution. Wherever we see an x squared, we've put a y. And so you'd factor this as y minus 1, y minus 5. And so you'd factor this one as x squared minus 1 and x squared minus 5. I can do a little bit better with this one because it's a nice difference of squares. The x squared minus 5 isn't quite as nice. I think I'll just leave it like that for a minute. So our conclusions, finding the x-intercepts, therefore x equals 1 from that first bracket, x equals negative 1 from the second bracket. From the third bracket, x squared minus 5 equals 0, which means x squared equals 5, which means x equals plus or minus the square root of 5. And this is a kind of a conflict for us. Writing it as the square root of 5 is exact, right? That's exactly the right answer. But we have to graph it. So if we have to graph it, knowing the square root is great because it's exact, but if we're actually going to plot it on the grid, we probably need to know that it's 2.34. So x-intercepts at 1, -1, and, oops, I missed it there, plus or minus 2.34. So -1, +1, and 2.34 around there, minus 2.34 is around there. So that's all I've got. And remember, those are just points, right? We don't know anything about maxes or mins yet. Those are just the points that we have. So there's intercepts done. The next thing in our algorithm was critical points. So to find our critical points, we were going to set the derivative to 0. So we need to find our derivative first. That'll be 4x cubed minus 12x. And we're going to have to save that because in a few minutes we'll have to take the second derivative. So remember what that one is. 4x cubed minus 12x. And if we're setting that to 0, and we want to solve, we could common factor, take a 4x out. Leaves you with x squared minus 3. So therefore x equals 0. Or this one isn't as nice, x squared minus 3 equals 0. So those are our three values. Whoops, I missed the square root there. There we go. So we have three critical points for this function. They happen at x equals 0 and x equals plus or minus root 3, which is about 1.73. Now, the last one when we did our x-intercepts, those are on the x-axis, so we know exactly where the points are. We would like to know the points here. So we have the x values, but we want to know the y values too. So we're going back to the original function to figure out what the point is. If x is 0, remember subbing back into this guy now, we get an answer of 5. Right? That was our y-intercept. We knew that point already. If we sub in the 1.73, or the square root 3, I suppose, if we wanted to be even more accurate. It's going to be a little squishy, isn't it? This time we were able to do it actually by subbing in the square root. Sometimes we can't, but I wanted to show you this one. Root 3 to the 4th. No, let me do this one first. Root 3 squared is 3. Minus 6 would be 18. So when I do root 3 to the 4th, you do root 3 squared first, which is just 3. Square that again is 9. So what's that? 14 minus 4, I think. Yeah. Now, if I do the other one, if I do minus 1.73, we also get minus 4. You can double check that, but that makes sense, I think, right? The minus sign made no difference here because I'm raising it to the power of 4 and the power of 2. So we have a very symmetric graph here, which is nice. It helps us a little bit for graphing purposes, makes it a little bit easier. I would like to put those on the graph now. So what was it? 0 and 5 we already have, right? That was our y-intercept. I'm going to mark it again, though. And then I have to remember 1.73 and minus 4. 1.73 and minus 4. That's about there. 4. About there-ish. I think that looks pretty close. Minus 1.73. About there. So those are critical points, and I'm going to put a green one there now too, because that's actually a critical point. Okay, now here's something you need to keep in mind. Now that we've got that, you can pretty much graph this thing, right? I don't know, I think you can. I think you can picture it. I'm still going to go through the process because I want to show you these next 3 steps. They're important, but they're going to be more important as we get to other functions which are more complicated. So that's where they become a little bit more useful. They also serve as ways to double check things as we go. So that's why they're there. We do need them. So granted, I do believe you can take a look at this and have a really good idea of what the function looks like. But we're still going to do a little bit more. So we found our critical points. The next step is called our intervals. Whoops, too far. It's called our intervals of increase and decrease. And this table at the moment is bigger than I need, but I sort of got it set up as a default one for whatever. What we're going to do is we're going to check to see if our derivative is positive or negative between the critical points. So we're saying, okay, between this critical point and this critical point, is the graph on the way down or is it on the way up? And as I say, when you looked at the graph, you already knew the answers to this. So bear with me. This is not, we're not doing it because we really need to for this graph. We're doing it because it's part of the algorithm for curve sketching and you need practice with that. For this interval section, we need to cover all ranges of the domain. So our critical points, or our critical numbers, I guess we could say, were there. Right? Minus 1.73 is the furthest to the left, 0 in the middle, 1.73, and then to the right of that. So when we talk about the intervals, I need to mention everything in the domain. So here's how we set it up. I'm going to first talk about everything to the left of that first critical point. So if x is less than minus 1.73, what does the graph look like to the left of that critical point? And then we're going to include the critical point. What happens right at that point? So I've made it to here. Well, the next interval is what happened in between. So I'm going to say minus 1.73 is less than x, which is less than 0. So I'm saying in between those two numbers what happens. And then what happens at exactly x equals 0. Then what happens between the critical points again? 0 less than x. And we're almost there. What happens at the critical point? And what happens beyond the critical point? So we have a fairly significant table. There's an awful lot here. Remember, our derivative was 4x cubed minus 12x. So when it says test value, what we're going to do is we're going to sub in a number that's within the interval. You can pick any number you want. The critical points are what divide up sections that will be increasing or decreasing anyway. So anything in this section works. So for this first one, you need to pick any number that's less than minus 1.73. You pick, I mean, if you want to, you can pick minus 17, but the smart number would be to pick minus 2. Right? Keep the numbers small, and it's less than minus 1.73. So that's a good way to do it. Jump ahead to our next interval. Between minus 1.73 and 0 would be minus 1. It's going to be a 1, and that can be a 2. Now for those other ones, there's not really a test value, right? Because there's not a number in between. So I'm going to put a little slash here, because we're not picking a test value. We were given a test value. We're wondering what happens at x equals minus 1.73. Well, I already know, right? We found out that those were critical points. We know that the derivative is there. That's how we found them in the first place. So those we've got. What we're going to do now is I'm going to sub in the minus 2 value here into our derivative. And all I care about is if the answer is positive or negative. Okay? Because if it's negative, that means the graph is decreasing. And if it's positive, that means the graph is increasing. Right? That was what we looked at last day. So if I sub in minus 2, it's 4 times minus 2 cubed. And I think I got an answer of minus 8 there. And the key wasn't the 8. The key is the negative. And since it's a negative value, this graph is decreasing. And that's what I'm going to put here. So when I have graph in the table, what I mean is, what's the graph doing? The graph is decreasing. It's on the way down. If I sub in minus 1, I have if I sub in -1, I can do that one in my head actually, that's going to be an 8. So positive 8 this time. Not important that it's 8, what's important is that it's positive, therefore it's increasing. If I sub in +1, I get a positive number, and I'm going to show you this time. I'm just going to put a plus down. Or, excuse me, I get a negative there, don't I? Wow. I get a negative if I sub in +1. So this is decreasing. And when I sub in 2, I get a positive value, so it's increasing. Now, the things that we've left out, obviously this part, we don't need that. Right here, if we've gone from decreasing to increasing, we must have hit a minimum, right? We've gone from a decreasing function to an increasing function, it must have been a minimum. Then we've gone to increasing to decreasing, so that's a max. And then decreasing to increasing must be a min. So that's how we complete that table. Now, there are no surprises here, right? This graph is going to go from decreasing to a minimum, to increasing, to a maximum, to decreasing, to a minimum, to increasing. And if we look at the graph, that I think is sort of exactly what we figured it would be. Oh, it doesn't work very well if I do that. It's going to go down, up, down, okay? And I didn't really want you to see that, so I can get rid of it anyway. But that's all that's happening. And that's exactly what those intervals told us, right? So again, no surprises here, no surprises. But later, when we start getting into a bunch of asymptotes, then we can have more issues. So that's why we're practicing it now. So there's our intervals of increase and decrease done. Inflection points. To do inflection points, and this is places where we're changing from concave up to concave down or vice versa, we need our second derivative, and we need to set it to 0. Remember, our first derivative was 4x cubed minus 12x. So our second derivative is 12x squared minus 12. And one thing that's nice is that the degree keeps getting smaller, so it becomes a little bit easier to solve each time. So we get two values. We get x equals -1 and x equals 1. Those are our two inflection values, I guess. Those are x values. We do want to know the points, but the -1 and the 1 should look familiar. Those were our intercepts. Those are the x-intercepts. So it turns out not only were they the x-intercepts, they actually did have some extra meaning. They're actually the points of inflection as well. So let's take a quick look at the graph before we do our intervals. So right here, that -1 and that 1, those are going to be the locations of our inflection points. That's when we're going to make the change from concave up to concave down. That's going to be tricky for us to draw. We'll have to be careful, but we can come pretty close. And certainly labeling them with a little IP there helps. For the intervals of concavity, we're basically doing the same sort of trick that we did with the intervals of increase and decrease. We're going to have a big table again, and this time we're only looking at values between our inflection points. So we're worried about x values of -1 and 1. Notice, I'm going to go back to the graph again for a second. If you just look to the left, if you just sort of look in this section here up to that inflection point, and again, you can picture it from here, right? That section, the graph is going to have to be concave up. And then as soon as it crosses the inflection point, it's going to turn to concave down. What's important is the change in concavity happens at inflection points. It has nothing to do with critical points, right? At this point here, that doesn't have anything to do with the change in concavity. It's still concave up there. So when we get to this section, when we get to our intervals of concavity, we're ignoring the critical points. We're only focusing on the inflection points. So I need to include all intervals again. So I'm going to say x is less than -1, x is equal to -1, between -1 and 1, and then bigger than 1. And certainly the fewer points we have makes this job a little bit easier, right? Test values, we can try a -2 again, try a 0, and try a 2. Oh, sorry, the second derivative, remember, was 12x squared minus 12. We don't need a test value here. We don't need a test value here because we know that the second derivative was going to be 0 at those values. If I sub in a -2, I'd get 12 times 4, 48. I'll get 36. But what's important is that it's positive. If I sub in 0, I get 0 take away 12, so -12. Important part is that it's negative. If I sub in 2, I get 36 again, but the important part is that it's positive. So as far as the graph goes, since the second derivative is positive, the graph is concave up. If we have a negative value, it's concave down. And concave up again. Now in the intervals of increase and decrease, I was able to say max and min for the points in the middle. I can't really do that here. It doesn't make a difference for us if it's going from concave up to concave down. We're just calling these inflection points either way. Okay. So the intent of those two tables that we made, this one here and the intervals of increase and decrease, is basically a check. It's for us to look back and go, okay, does everything else that we have in our graph match up with the calculations that we've done here? If you think about the number of calculations that we've made now, there have been a lot. We've had to do an awful lot of calculations in order to make this graph. So the tough part of this unit is getting through all of those calculations quickly enough without making mistakes. And that's why we're going to practice for a while. Hopefully you got those tables handy. I know I can't pull them up quite as quickly, but if you take a look at those as we try and make this graph, it should help a little bit. For example, in between those two inflection points, the graph was supposed to be concave down, and it's increasing at first. It's going to look kind of like that, and then decreasing, but concave down the whole time. So it's going to look something like that. To the left of it, I know it should be concave up, still decreasing for a little bit, but here's concave up. Hit the critical point, which means I'm changing direction. Graph looks like that. And remember, from everywhere from here to here, that was supposed to be decreasing, and we see that, right? The graph is going down. On the other side, it's going to look like that. And the hope, I didn't do a terrible job. Critical points are more obvious, right? It's clearly switching from increasing to decreasing or vice versa. The inflection points, you're trying to make it look like we've switched from concave up to concave down. It just becomes really important to label it, right? So at least that part's labeled, and then do your best as you're making the graph. Okay, and let's take a look. That's the real version there. So mine's pretty close. It looks like I've got the curves maybe a little bit too steep around the inflection points, I would say. But we hit all of the right values, right? So that's what it looks like if we're trying to do a complete version of a curve sketch for a polynomial function. So the polynomials aren't too bad. The derivatives are relatively easy to take. Next little while, though, what we're going to start adding in is the rational functions. With rational functions, we're going to end up with asymptotes. So we have to be more careful with the asymptotes. Because of asymptotes, we're going to have to be much more careful with our intervals of increase and decrease and our intervals of concavity. So it just adds in a little bit more. Plus, and if we have a rational function, the derivative is going to be much harder, right? And that's why we practiced so much with that in the last chapter.